Okay, now we want to calculate the field on a 10-centimeter loop. And I pulled out the Helmholtz coils. We see a coil about this big around. That's a coil with radius 10 centimeters. And we'll see in lab just how important the Helmholtz coils are. Okay, so we've got a 10-centimeter loop, and we want to find the magnetic field at the center of the loop. I didn't specify where the loop was or what its orientation was. Just left that to you. So what I'm telling you, and then what I told you, is you should choose the origin of your coordinate system, because you're going to want to put a coordinate system on this. Okay, this is a vector rule. You're going to want a coordinate system. Now you can kind of think around the coordinate system for this situation, but I really want you to get used to thinking in terms of the coordinate system before you start trying to think around the coordinate system. Okay, 10-centimeter loop. I instructed everybody to choose the origin at the center of the loop and choose which axis goes through the center perpendicular to the plane of the loop. Very simple. Okay? So you could draw anything. Okay, I drew this. I put the y-axis in this direction just because I didn't see anybody doing that. I put the z-axis here and the x-axis here. It's not where you're used to seeing them, but you know, if you kind of pull this thing down to where the x-axis is in the horizontal plane and then rotate it around, the y-axis is going to go where it needs to, and the z-axis is going to go straight up. And you want to be able to visualize that. You want to convince yourself of that. So there is an example, and the origin is at the center of the loop, so here's the loop. It's very clear that the loop is in the xz plane. Now everybody eventually came up with a picture very much like this, but with the x-axis or the z-axis in this direction, and you know, the other axes. As long as you have a right-handed coordinate system, it's going to work. Okay, that right-handed coordinate system just means well, it's just a cross product. X cross y has to be in the z direction and so forth. Okay, then I said choose an increment delta L by specifying its position and direction. Now we're going to keep the delta L as the magnitude of the increment, but you have to choose an increment somewhere on your loop and specify its direction and its position. Where is it on the loop, and what therefore is its direction? Well, people took a while to do this, but ultimately most people decided, okay, I want to choose my increment to be out here along whatever axis they happen to put here. Okay? And some people chose up here. That's all right. You could have chosen here, 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 or here, and those would have been easy choices. Now you could have chosen some other position in the circle, but since I just asked you to choose any position, well, there's something to be said for choosing an arbitrary representative position. Okay, but I think in my instruction, at least verbally, I said choose an easy place. These are the easy places, and everybody chose either this one or this one, which is exactly what I intended. Now, some people chose things like, okay, the x-axis here, and this is at 3 o'clock on the loop. 3 o'clock on the loop is perfectly good. The picture showed me exactly what it should have showed me, but 3 o'clock on the loop doesn't specify a vector. Okay, so, because, you know, what do we want to do? We want the position and direction of our delta L vector. Okay? Now, if you say, as in this case, that the position is at the point 0, 0, 10 centimeters, or even on the z-axis, on the positive z-axis, that would have been okay. Now, if this position is on the positive z-axis, then of course you want the loop in some plane that includes the z-axis, then you have to decide what's this direction. Well, how do you decide a direction of a vector? The easiest way to do it is to choose a unit vector in that direction, usually. And that's especially true if just one of the I, J, or K vectors is involved, which it is at this point. So, what is the vector in the direction of this little arrow I drew? Well, this little arrow is in the direction of the positive x-axis, so that's going to be the I vector. Delta L is therefore going to be delta L times the I vector. Now, people having had multivariable calculus, I kind of said, you know, what moron taught you multivariable calculus if you can't do this instantly? Then I realized that I'd taught the multivariable calculus. Well, that's okay. And I also said that's why I temper my criticism of people that have taught courses where you don't bring in what you're supposed to. Okay, so I know it's tough, and my students aren't all that much better than anybody else's, if they're even as good. So it's a tough sell when you're trying to accomplish the goals of the course. Now, of course, one goal of multivariable calculus is that people be able to come out and do this, but it doesn't happen, and it doesn't happen with people that took multivariable calculus under other people either. So we've got the increment, we've got our delta L. It's delta L times I. Our delta L vector is our delta L magnitude times the I vector. So now we've got a delta L to put in here. Now I did give you a current, you know, that's almost incidental, we just throw in the current. And the current I think was again 50 amps. So that our I delta L is 50 amps times magnitude delta L times I. What's our R vector? Well, by the definition, which we got last time, you should understand the R vector goes from whatever incremental current you have to the point at which you're trying to calculate the field. We're trying to calculate the field at the middle. So where's our R vector? Well, it goes from our increment to the center. And if you choose your increment so that it includes the point on the z-axis so that you can use I as your direction, this vector is just going to be the vector along the z-axis in the case of my example back toward the origin. That's going to be the vector negative k. And the R vector has a definite magnitude. It's 10 centimeters times negative k, which is, of course, negative 0.1 meter times k. Now here, my writing gets a little hard to read, and then I progress from here, back to here, back to here. So I'm going to stop this video here and start another one, and I'll work it out over here on some clean board space that I have available. So I'm going to work this out, even though it was already worked out, so that you can read it and so that you can follow the steps. Okay, I'm going to just work it out. I'm not going to work it out in advance and point to it. I'm going to work it on camera. And you should try to work it yourself before you watch me do it.